I'm Cully, aka Flossy Purse, and this is Dominic Torno, a OG distributed systems expert, and we're
Oh,
talking
thank
about
you. Thank you.
all things distributed systems with a slight or heavy emphasis on Resonate HQ, the software that should help make building distributed systems a delightful developer experience. And I'm just sending out some tweets here. Cool. So I'll probably put one up on LinkedIn too. But before we do that, um, what what was our topic? We were talking earlier about a bunch of different things. We were talking about event-driven architecture. We were talking about transactions. Um, we've been talking about Resonate specifically, and how how the distributed event loop will solve so many problems. What's what's been like a top thing on your mind that you would love to dig your teeth into and start talking about?
I want to talk about the transactions versus durable executions. Right?
Okay,
Because the
yeah.
durable executions, they have been dubbed as the new transactional stack, right? So that basically means that the term transaction was used as a like defining characteristic of durable executions, right? So there had to be some similarity, something that triggered that idea that database transactions or that durable executions are akin to database transactions, right? So what durable execution is for a distributed system, a transaction is for a database, right? So that's basically what that term, the new transactional stack, like implies. Right? But then it's super interesting to look into it, like what is the difference between transactions and durable executions in terms of like guarantee? What can they provide? Let's look at what a transaction and a durable executions, what they are, right? So it's like you can argue both of them is a sequence of operations, right? A transaction is a sequence of operations, and the durable execution is a sequence of operations, right? So they have a very they're very similar in nature. Now, a transaction formally is a sequence of operations that end in exactly one commit or exactly one abort. Right? If the transaction ends in exactly one commit, it is as if the transaction has executed to completion in isolation, right? And if it ends in one abort, it is as it not executed at all. And for durable executions, we don't really have that. We don't really have that like equivalent. You can still argue though, because especially for Resonate, durable execution is just a normal function. You can still argue that it's a sequence of operations, right? Other function calls, whatever you do in that function. And it ends in a terminate, right? And a terminate can either be a successful termination or an unsuccessful termination, raises an exception. But there is also the possibility of a crash. So that is true for both a transaction and a durable execution. When the database crashes in the middle of a transaction, right, we treat it as if it was aborted. And but for durable executions, that's a little bit more difficult. And then we can get into why in a moment. But so that's basically sequence of operations, right? So,
Can I
but
ask you?
let's look.
Can I ask you? And I don't mean to interrupt
Mhm.
that train of thought specific, but you were, I feel like, one of the voices that helped focus in on the term durable execution as the like term to describe the new abstraction that is coming onto the market in in terms of in the distributed systems industry, right? What like what and I know you're not like one to throw around terms so much. So like there's obviously like some criteria in place that you sort of focused on to like determine that that was a good term and that there were some boundaries in its definition, if that makes sense.
So for the durable execution, I did look at some of their like core characteristics, right? And that durability of progress, right? So that in the loosest sense possible, that progress is persistent, right? Progress is durable. Is a defining characteristic of the durable executions. That's why I honed in on that particular term. I also previously did liken durable executions are to distributed systems what database transactions are to databases.
Yeah.
And there is a very specific reason for that one. So it's like much more than just like hopping on to one of the defining characteristics of durable executions. It's like, why do I make that comparison? Database transactions are one of the most successful abstractions the software engineering ecosystem has ever introduced. Right? There are some abstractions that are just beyond incredible. If you look at operating systems, processes, for example, right? The process, it gives you the illusion. It gives you an illusion equals developer experience here. It gives you the developer experience that your application owns the CPU. Together with virtual memory, right? It owns the CPU and the memory in the machine. Even though there are other processes that are also on that CPU and on that memory, right? It's an absolutely fantastic developer experience. The transactions similarly successful, whereas you can argue, arguably, right? So it's a matter of taste somewhat, but even more incredible developer experience. And that developer experience that can be like captured as happy-go-lucky, worry-free, right? As soon as you cross that threshold from your code to begin transaction, right? It's like, oh my God, worry-free. Yeah? It's like all stress is gone. You basically just have the guarantee of correctness. All right, that's don't worry about it. We'll fix it. We gotcha. Yeah? That's what a database transaction is. We often classify it or describe it in terms of ACID, which is, by the way, an absolutely fantastic term and acronym, because it has taken over the entire ecosystem, right? And everybody describes what is a transaction in terms of ACID, like atomicity, consistency, isolation, and durability. But I think it somehow doesn't do it justice because it doesn't capture that like developer experience, that feeling, right? Cross the threshold of begin transaction and you are guaranteed correctness. Right? So that is absolutely amazing. And so why did I then link the term transaction to like durable execution?
Yeah,
it's because we want to provide you a similar developer experience, right? Whereas like worry-free, just like we gotcha back, yeah. But that transactions, yeah. Oh, I'm sorry, I didn't want to interrupt.
Oh no, but as we've talked about, right? Like we have since discovered that like there's so much more nuance there, right? There's like,
oh yeah,
there's way more caveats and or assumptions you have to make for that to be true, right?
Yes. Yeah. That's a big one. All right. So it's like database transactions are in a position to make a lot of guarantees and actually not asking for much or anything in return. They just give you that guarantee. Oh, but durable executions, distributed systems, they ask for so much. And you cannot abstract it away. Distribution is an irreducible property. You cannot pretend that a system is not a distributed system. So, and let's look into why, right? Why is that the case? So one of these prerequisite, you can say, to correctness is completion, right? You got to run to completion. If your transaction or your durable execution consists of 5 steps, then after the first step, you're potentially in an intermediary inconsistent state. After the second, after the third, after the fourth, and only after the 5 are you once again in a consistent state, right? Potentially. So now, correctness requires completeness. It's not enough, right? It's not enough to just be complete in order to be correct, but it's a big chunk. So, and it's definitely necessary. So, and that's captured as atomicity, right? And atomicity has two different possible interpretations. One is that it runs all or nothing, right? That is failure atomicity. Or it runs 5 executions as if it was 1 execution, right? That is this indivisible interpretation of atomicity. Databases capture that as isolation. Right? So, well, in durable executions, we can provide you isolation because we don't own all of these target systems, right? If you use a durable execution to make a bunch of service calls, we don't own the downstream systems, right? So if we change the state of one system, but not the state in the second system yet, right? We cannot pretend to be isolated. So that's or not pretend, but we can't be isolated. It's very difficult. So let's hone in on that failure atomicity, right? Where say we run to completion or not at all, right? All or nothing. Oh man, databases, they have an advantage here, a big advantage. Why? It's actually very simple. Very simple to point out why the database has a massive advantage. And this is twofold. The first one, a database transaction isn't a sequence of arbitrary operations. A database transaction is a sequence of reads and writes. All right. And the thing is, I know the semantic of reads and writes. Number 1, read doesn't change the state. And number 2, write changes the state. And I know exactly how it changes the state. Right. Let's say I have a database consisting of, we're now interested in a transaction, 2 database objects, X and Y, right? And X at the start of the transaction is 3 and Y at the start of the transaction is 4. If I now say X is 5 and Y is 7, I know the semantic of that right? So, and also very importantly, I know how to undo what I just did. If I set X to 5, right? I can already, like in the back of my head, basically on a journal or write a hit log, I can write a compensating action, meaning I can say set X back to 3. Right? So now, if I go through the transaction, I set X from 3 to 5, and then I crash, meaning I abort the transaction. On the recovery path, I can now look into the compensations, set X back to 3, right? And therefore I undid what I just have done. And the database is in the same state as if the transaction didn't run at all, right? So the biggest part is we know the semantic of the operations, and we can automatically already collect the necessary operations to bring the database back to the original state, therefore guaranteeing the not at all semantics, right? It's like completely or not at all. We can do that on a platform level. We don't need your cooperation for that, all right? Database does that. It doesn't matter what the developer writes in their transactions.
Right.
Absolutely not important. We don't have that luxury in durable executions. We just call a service. What's the semantic of the service? I don't know. This is like, what's the semantic? It's like I'm calling a generic function that is basically like reserve hotel room or book hotel room, book flight, right?
Yeah, you don't know what's it's changing on the other side, right? You don't know what's happening.
Not even little, right? I have absolutely no clue.
Yeah.
And I cannot like generically like register compensations for that, right? It's not happening. So I need the cooperation of the developer, right? And it's like the best we can do is ask the developer for every step that we are taking to register a compensating action. But also keep in the back of your head, we don't even know that a compensating action is a compensating action. But on a platform level, it's just another action. Right? So it's like, it's just something to do on a platform. So
it would have to track the changes that were made and make doing an intelligent change to compensate, basically. Like there's a lot.
Nope, that happens in your head. Yeah, you're right though. In your head, that's true. But on an application level, all we know is we call it function X, right? And then the developer registers function Y, right?
Yeah,
that's it.
To compensate.
We don't know what X is. We don't know what Y is.
Yeah.
But you're right. As a developer, that's where we need your cooperation. You have that in your head. X is book hotel room and Y is cancel hotel room. And we are hoping for the best. All right. We're basically just hoping that canceling that hotel room will undo whatever we just did. If that's not true, there's nothing we can do about it. Okay, so that's number one. Big advantage database. But there's one more thing, and they go hand in hand. Super, super important. So the database crashes in the middle of a transaction, right, and is now in an inconsistent state. How are we always saying that a database is never in a consistent state, in an inconsistent state? A database transitions from a consistent state to a consistent state. We say that, right? But it's not true. So not even a little bit, right? If I have 5 steps in a transaction, the database transitions from consistent state, inconsistent, 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 inconsistent to consistent, right? So if it crashes, it is in an inconsistent state. No if, else, or but. It is currently in an inconsistent state. Huh? Why do we keep saying that a database is never in an inconsistent state? Because the database does not externalize an inconsistent state. Externally observable are only consistent states. So if the database crashes and then starts, it will not answer a single query. It won't until it successfully runs through recovery. If it turns out that the database cannot run through recovery, it will refuse to answer any of your queries. No read, no write, because it can't guarantee that the answer that you get is consistent to its state before that transaction. It can, right? Therefore, it refuses to answer. It refuses to externalize its state, making the inconsistent state unobservable forever until a human operator comes in and fixes whatever needs to be fixed. So this refusal of externalization, right, is a big part of what makes transactions correct, overall correct. Because now the database goes through recovery until it goes from bad to good, and then it starts again. All right. So now let's compare that to durable executions. So first off, we already figured out that this whole Saga compensation angle is hey, best effort, if so, and it's like requires the developer's cooperation. Nothing we can do about it. Mm-hmm. All right. Now we had 5 steps. We crashed after 3. Now we have to execute 3 compensate. What if we can't? What if we cannot execute these compensations? One of the compensation keeps failing. Now what? What are we going to do? Remember the database? The recovery kept failing. The database didn't do nothing. You send a query to it. It said, not now. All right? I am not in the right state of mind to answer your query. Once again, there's nothing we can do about it. that durable execution is now in a state where it keeps retrying until it runs out the retry budget. One of these compensations, the compensation never goes through. The system as a whole does not refuse to externalize its state. It is in an inconsistent state. All right. I have no booking in the system because we just canceled that. The flight is already canceled, but the hotel is not. Right? And there's no way to not externalize that.
Right.
That money is gone from your credit card. That hotel room is booked in the hotel system. If you call the hotel and ask if you have a reservation, the hotel will say yes.
That happened to me when I was recently this fall. My wife and I went on a cruise, and I went to go book like one of the side expeditions or whatever, and totally like I'm pretty sure my credit card, it went through the whole process, and I received this error, and it was like, we're charging your credit card, and then it just hung, and was like super unclear. Finally I got a notification my card was charged, but then like the booking never showed up, and I had to like call into support, and then they're like, oh yeah, you did pay for it, and then they added it back. It was a pain in the butt.
And that is exactly why, because it's not a transaction, right? So it's like the transaction would refuse to externalize any inconsistencies. But if you have like an orchestration problem where multiple systems are involved, one is in that state, one is in that state, both of them are in a consistent state for themselves, right? But in combination, they're in an inconsistent state, and then we are the ones dealing with it. Mm-hmm. And I had a similar experience with an airline where booking a flight ran into errors and continuous retries, and my credit card got charged multiple times. And the flight is not cheap, right? So it's like the credit card got charged multiple times. So obviously I called in, and them saying, don't worry about it. Yeah? So we run, yes, we see it. The ticket is only issued once, and these charges will disappear within 24 hours because we run cleanups, basically, right? So it's like they fix it after the fact. I was like, luckily it was not like exceeding the credit limit, but that has real consequences, right? So at that point, it was fine.
Yeah, but it's also an interesting example of how people go and attempt to solve these issues, right? There's lots of ways, but that's one of them. Like, wait till all the disaster happens, let it ride,
yeah, and then clean up,
and then we'll go clean it up after.
Yes, absolutely. Which also is one of my greatest learnings. Retries are your friends, but also your enemies. Yeah? So it's like retries are frenemies. Yeah.
Yeah.
With retries, you can achieve forward recovery, right? You fail somewhere in the middle, and then you retry that, and then you run to completeness. Yeah. But if that is not done perfectly to the T, yeah, then you also run into the issue that you may have forwarded, recovered, and achieved completeness, but still not correctness, because retry itself is what introduced the incorrect behavior.
Yeah. That's a pain.
So then as a summary, right, you can look at like, okay, database transaction, absolutely fantastic developer experience. It's like, for me, unmatched, because as soon as you cross the threshold to begin transaction, right, you live worry-free. It's incredible. It's an incredible developer experience. Now we want to replicate that for distributed systems. Turns out to that level, we cannot, right? But that doesn't mean that we stop trying to get as close as possible, right? So for me, basically, a transaction sets a gold standard. I have not seen like another abstraction that has an equal appeal. But again, it's a bit of personal taste, but that has an equal appeal. And that's basically our gold standard that we strive for when we implement distributed async await. But it does turn out that there is like, in order to give you guarantees, in order to give you, for example, completeness guarantees, right, correctness guarantees, there is a lot of ifs involved. right? So it's like, we need your cooperation. We need a lot of prerequisites that you as a developer, and as an operator, you have to meet, right? So, for example, we rely on progress. Database transactions don't really, because they, again, don't externalize, right? If you pull the plug of a database system in the middle of a transaction, never plug it back in, database is fine. You cannot ask it another question. It will never externalize an inconsistent state. The last state that it externalized was perfectly consistent. Thumbs up. All safety guarantees completely achieved. Yeah? Now, with the durable executions, we say, hey, we guarantee to run you to completion, right? There's a lot of ifs in there. If I pull that plug, nope, right? So I say, if I pull the plug and never put it back in, we won't. And I say, oh, but then it's just the same with the database transaction. Because now the system as a whole is possibly in an inconsistent state, right? The service A is in a consistent state in and of itself because it makes sure of that. Service B is in a consistent state in and of itself because it makes sure of that. But as a whole, A reflects something that B does not. So you're in an inconsistent state. And thanks to you never putting in the plug, that's not going to be resolved, right? So we rely on your cooperation as a developer and an operator to meet a lot of, like, to check a lot of checkboxes, and then we can give you completeness guarantees, right? But only then.
So yeah, what's interesting is that I feel like I wouldn't say they necessarily do this outright, but there's a lot of like, you don't have to worry about this, or you don't have to worry about that type of messaging with durable execution systems. But really, it's not, you're not being really absolved from having to have a really solid functional requirements checklist or outline of your functional requirements and the exact behavior that you're trying to achieve. It's just that you're trying to now achieve a particular behavior with this other type of abstraction, right? But yes, as you're saying, like, we need your cooperation being like, you're not absolved from still understanding and specifying the behavior that you're desiring.
You're entirely correct, and I'm very disheartened and also distraught by the lack of nuance in the conversation, because it's like I personally, when I put myself in the shoes of a consumer of a certain abstraction, and I'm in the shoes of a consumer all the time, right? Then it's like I appreciate to get a nuanced picture, because only then will I be able to take that abstraction and build correct by construction systems, right? Otherwise, I imagine to have guarantees that I actually do not have. Right? And so then I am personally disheartened by marketing messages. I need engineering messages. Yeah? And for durable executions, there's a lot. And again, there's a lot that Resonate cannot do for you, and no other company can. All right, they can't do it for you. So, but I really want to point out, what can we do, right? What can we offer you? And then where do we require your input, right? So that then holistically, in combination, right, you get a correct system. And we also spend a lot of time trying to give additional tools, like, for example, deterministic simulation testing. So you can test, right, under these various scenarios that can happen if your system is still correct, right? So for example, our Python SDK has it already built in. Any Resonate function, you can deterministically simulation test that function, right? And then you can see if the invariants that you specify are met under these different concurrency and distributed conditions, right? The failure conditions and the restarts. So, because again, databases, if you look at the I in databases, the isolation, that can guarantee you like the absence of a lot of problems, like for example race conditions, right? Because the serializability guarantees that the database is in a state as if either transaction 1 happened before transaction 2 or transaction 2 happened before transaction 1, but not that they happened at the same time, right? Even so they're executed at the same time, the database has to be in a state where one executed before the other. That's not true for distributed systems. They don't give you that guarantee, right? So you have to implement all kinds of it's not workaround, let's say patterns, like for example, optimistic concurrency control or optimistic rollbacks in order to get similar behavior, right, or similar results. So, but again, no distributed or no durable execution platform on this planet can do that for you. Yeah? So we give you the tools to at least check, right, that the code that you build there meets this criteria, right? So you get that, but you can get very high confidence that what you did is right, right? But we actually cannot make it right for you.
You mentioned the DST a bit there. I think that that's fascinating because if I understand it correctly, and I'm still wrapping my mind around all this, so forgive me. But what's really cool there is you can, and first the biggest difference between my normal experience with having a deterministic function and the DST that Resonate offers is that previously I was dealing with workflows where you had to concern yourself with determinism at the function level, like within the function itself, that's deterministic. But if you place that function next to another, that workflow with another workflow, and they're both doing things operating on the same set of resources, there's like just no way for you to know if what you're doing has the behavior that you want, right? But with Resonate's DST, you can get close to understanding that behavior. Like you can basically check the determinism of the system as a whole by feeding it like tons of different inputs, and seeing how the behavior lines up, right? By obviously we need your cooperation as a developer in that to tell us what behavior you're expecting and what you're not expecting. But with that level of cooperation, you can actually like get to some level of understanding of whether or not your system is behaving correctly under like a wide variety of inputs, right?
Yes. So what we do with DST is so we utilize the determinism of your code, right? Your functions, and the DST offers a deterministic scheduler, a pseudo-random but deterministic scheduler, so that we can interleave your workflows in different execution orders. Workflow 1, step 1, workflow 2, step 1, workflow 1, step 2, workflow 2, step 2, and so on. Yeah? And then we can mix and match, and basically just mix. Then we mix that up and see if the invariance that you specify, you still have to specify the correctness criteria, right? Because generically, we don't know what constitutes correctness. It's once again different from databases. You can just generically define that. To a certain degree, but you can also, as a user, specify consistency guarantees, right? So it's like, I never want this column to be less than 0, for example.
Right.
So you specify your invariance, and we run a lot of different like interleavings, and see if your invariants are all met. If they're all met, and you run this like thousands of times, there's a very high confidence that it's correct. Right? This is like classical race conditions. A race condition is where the correctness of your system depends on the execution order. right? If there is some execution order where the system shows an incorrect behavior, then you have a race condition. So our DST can basically, since it interleaves in a lot of different permutations, it finds race conditions.
Yeah, that's cool.
And race conditions, so if you look at modern systems, you basically have two adversaries. You have concurrency and you have distribution. Right? These are two very difficult to deal with adversaries. Concurrency introduces a non-deterministic execution order, partial order, non-deterministic execution order. That is what, for example, causes race conditions, right? Where it's like, hey, if A happens before B, it's correct, but if B happens before A, it's incorrect. So what's our, as developer, what can we do? Well, we have coordination. We have coordination primitives. And Resonate uses one of the most popular coordination primitives, that's promises, right? So functions and promises. Promises are synchronization barriers. So with promises, you can coordinate your executions. So that's our first ally in the fight against concurrency. And then we have distribution. Distribution introduces partial failure, right? And that is where like non-deterministic partial failure. One component fails, another component keeps going. And what is our ally here in the fight against distribution? That's recovery, right? So we recover. And generically, the best thing we can do is basically we retry, we restart and retry, right? And so for Resonate combines both of these capabilities, right? So we have a distributed event loop that's responsible for the coordination, the event loop protocol, and we have a distributed task protocol that's responsible for recovery. But again, in order for this to be correct, unlike with databases who don't need you to do anything, we need you to do a lot, right? So we need the code to be correct. And to check if the code is correct, we give you the DST, which simulates the effects of concurrency and which simulates the effect of distribution by running your code in different execution orders and also crashing your code at different points in time, and then retrying the code and see if you still meet all of the invariants that you specified. And once you meet all invariants, we consider your code to be correct, and you can consider your code to be correct.
It's pretty awesome. I think I always like the explanation you give, talking about the simplicity of functions and promises, going from a single node, if you will, right? And then adding nodes, going from async await to distributed async await, and how just the elegance and simplicity of that. Because I think it's, we're dealing with we see a lot of these other durable execution platforms out there that are like also trying to provide a solution for the same things that we're just talking about: concurrency and distribution, right? Those are the adversaries. And there's like others who are also trying to go after that. But they have inadvertently added more complexity in the types of solutions that they're bringing to the table, right? It's not just like, we need your help as a developer to think about these requirements. We also need you to learn a brand new paradigm and way of thinking about code and writing code in order to do that. Whereas distributed async await builds off a typical async await programming model, right? Which lots of developers are familiar with. If you're in Python, and TypeScript, JavaScript, right? And some of the others, it's like the same thing but called something different. You got coroutines in Go. Like, you've got async and await, and it's like something a lot of developers are familiar with. And so what's really elegant is going from that to distributed, right? And tackling those adversaries with something that people are already familiar with and building on that. And I think like, yeah, I don't know. I would love to hear your explanation of that.
I'd love to be able to take to claim responsibility for the simplicity of functions and promises, but unfortunately, I'm not the one who came up with it. Yeah, so I'd love to take credit. But so we had functions since the 1960s. One of the Big Bang papers of computer science by McCarthy in 1960 introduced functions. And what was like a major, like in my understanding, a major achievement was the recursive nature of functions. Functions can call other functions, right? And so functions can call functions, and you can build even the largest systems from the smallest building blocks. Right? They compose recursively. We take that for granted, right? So it's like I remember that I was introduced back in school when it's like they give like very, very simple programming lessons, right? So you're introduced to functions and the fact that functions can call other functions as if it was nothing. It's amazing. It's an amazing feat, the recursive composition. And then in the 70s, when like concurrency was more prevalent than in the 60s, it wasn't everywhere, but it was more prevalent. The notion of a promise was born, right? It's like, and there's a certain duality. You can either say a promise represents a future value, right? Something that doesn't exist yet, or it represents an in-process execution. It's like a yin-yang interpretation, or wave particle duality. It's sometimes good to think about it like that. Sometimes good to think about it like this. And with promises or with functions and promises, you have the universal abstraction for computation, do some stuff, yeah, and then coordination, wait on some stuff, right? And with that, you can build the largest systems, right? From the smallest to the largest systems. It's an abstraction that recursively composes without any boundaries. So it's amazing, right? And so that happens like locally on a node in each and any programming language, right? Or not each and any, but some. So this functions and promises, basically async await, is a concurrency model for a lot of languages that are out there. It's a very popular one. So it's JavaScript, TypeScript, Python, Rust, Kotlin, C#, F# is everywhere. Now Golang took a different approach, right? They use communicating sequential processes as their underlying concurrency model, but async await as an underlying concurrency model is very, very popular. And it's very simple, right? It's only two abstractions. And but they are quote unquote confined, right, to a single node. So if you look at an async call graph, right? So it spans this call graph, and an async invocation and awaiting, so invoke and await, are two first-class relationships in these call graphs. The two relationships, right? One execution starts another execution with a promise as an intermediary, and one execution waits on another execution again with a promise as an intermediary. These are the two main relationships, but they stop at the machine boundary, right? So if you call a remote service, for example, via HTTP, it's not that spans another relationship between an execution on this machine and an execution on that machine. That's not what's happening. There is one local, and that's basically let's say HTTP fetch, right? So, that fetch represents another call, but that's not part of the call graph. The call graph doesn't know that, right? Mm-hmm. The call graph stops at fetch. Done. It's over. Yeah? And So that obviously makes a remote call a second-class citizen. It's not a first-class citizen anymore. The call graph doesn't even know it exists, right? And so we extend async await and make a remote function call again a first-class citizen, right? So and with that, we basically just take the programming model that is like it's already well known, well understood, well liked, right? And make the cross-machine communication, right? The inter-machine communication to a first-class citizen, just like the intra-machine communication. Right? We're not trying to hide the fact that a distributed system is distributed. You have to know that, right? Because you need to architect your system accordingly. But we give you the same call syntax and same call semantics as far as possible, so that you can seamlessly compose your applications also across machines, right? And we even use the same protocols. Whereas, like on a local machine, you have a local event loop, and that event loop works basically via callbacks, right? So awaiting on a promise is registering a callback on the promise that will be executed by the event loop when the promise completes. Now, wherever you call a function on a local node, you basically have to send a message in a distributed system, right? Because you cannot directly call a function, therefore you need to send a message. So that's exactly what we do. And our entire protocol, the entire event loop, the distributed event loop, relies only on two messages: invoke and resume. With these two messages, you can compose concurrent systems, even across machines, where the cross-machine relationship is a first-class citizen once again.
Yeah, that's pretty sweet. And it kind of dawned on me the other day when I didn't realize the power of it until we were talking the other day, and we got into how simple the specification was, like, because it's an open specification, right? For those listening, following along, it's all built on this open specification. You can check it out in the GitHub repo, Resonate HQ, open spec. I think it's durable promise specification.
Yeah, durable promise specification.
And it's like arguably different, right? Because you've said it yourself. Well, if everybody just did the way I wanted them to do, it would all across the board.
Easy, right?
Right. And then it's all easy.
Yeah.
But however, typically that's very complicated. Typically, like the way somebody wants you to do things is not exactly the way you want to do it, or it's much more complicated than it would first make out to seem. And the difference being with the durable promise specification is that it is fairly simple, arguably, right? And hopefully we don't shoot ourselves in the foot by saying that, but in theory, right, it's a lot more simple than a lot of the protocols that we've seen, such that if you didn't want to use Resonate, or you didn't want to use, right, you could go and store durable promises, however you see fit, using this specification, extending the boundaries of services and applications to become first-class citizens in that way.
Exactly.
Right? That was really powerful.
For the ones old enough, now I'm dating myself. If you think back at like open specifications, like for example the Web Service Description Language (WSDL), or for example SOAP, right? These are open specifications, but by God, try to implement that thing.
Yeah,
right? So it's a massive standard.
I almost quit.
Massive standard.
I tried to use a SOAP API one time. It was just awful.
It is an awful experience just using it, and then imagine implementing that. And imagine implementing that from scratch. It's just like, no. It's like, hell no. The durable promise specification, it has 4 method calls: create, cancel, resolve, and reject. All right, that's basically, that is I want to say, as simple as it gets. We have an exhaustive specification, transitions, an exhaustive table. We use that to generate an exhaustive list of test cases. So with that exhausted list of unit tests, you can even check that your implementation of 4 methods is completely specification compliant. All right. So, and again, it's 4 methods. It's really not that hard. So again, yeah, I don't want to shoot myself in the foot either, but I want to say it's as simple as it gets. Yeah. And yes, if you implement that, right, you don't actually have to use any part of Resonate. Yeah. So you can just implement that specification yourself. So as an example, right? Let's say so you're building a distributed async await app. Let's say you're building it on Resonate. You're using the Resonate SDK. You're using the Resonate server. But now you want to integrate, for example, an Apache Airflow workflow, right? So from your code, you want to kick off an Apache Airflow workflow and then wait for it until it completes. Yeah? Well, the Apache cluster offers what they call DAGs. A DAG is basically a workflow in their terminology, and then DAG runs, which is it's a workflow instance. And they already keep all of the information that is required, right? They already have a persistence. So what you can do is basically you put a proxy in front of it. It's like I have one prototype. It's like 70 lines of Python code. It's nowhere production ready, okay, but it's just a prototype because I wanted to play with it. And you can then map these 4 operations of a promise onto API calls for Apache Airflow. Right, so it's like then create a promise maps to start a DAG run, right? And I mean, again, it's 4 of them, so it's like do that, and then natively from your code, you can basically in JavaScript or in Python, you can just say call this function, which is now a function, right? So it's like which triggers the Airflow workflow, and then you await on it, you sleep on it, even if it's like 8 hours, right? So it's like, because it's usually Airflow workflows, data workflows, right? That may be very involved, so may have to wait a long time, and then your function on the one side just sleeps, and as soon as that thing is done over there, it starts up again because it natively integrates into the event loop because it's now a durable promise, right? And even our internal protocols we didn't release a spec yet, but even our internal protocols, very, very simple, right? So the the distributed event loop, 2 messages, invoke and resume, right? That's it. With these 2 messages, you get the coordination aspect. So you took care of concurrency. And then we have a distributed task framework that is responsible for reliable message delivery via a protocol, via transport of your choosing, whether it's HTTP or some message queue that you want to use, and reliable message processing via heartbeats, right? And if that is, so it's a distributed supervision and failure detection framework. If that finds that something crashed, it will basically reschedule it, right? And these 2 protocols are layered on top of each other. The distributed task framework is the same thing. It has like 3 or 4 messages. I forget how many, but it has like 3 or 4 messages. Each and every single component is meant to be dead simple, right? It's not just dead simple to use on a dead simple API layer. That's not where we draw the line. We want the implementation to be dead simple. Right? And that on each and every layer. So each and every of our protocols itself is dead simple. Right? So that there is really a chance that you can pick whatever part you're interested in, and you can even implement that yourself, right? Because if I tell you today to implement WSDL yourself, you can do it, but it's like your chances are kind of low, right? To get that right. And then you probably don't get the return on investment. But our standards are so small that you can get that right, no problem. And the return on investment, then depending on what you want to enable with that, is just there because it's so little effort.
Sweet. That's pretty sweet. I think that was something that when I started wrapping my mind around that, it made me really excited. Made me really excited about this,
So last remarks here, but it's like this idea of like dead simple, right? It resonates so much with me because I am never more distraught than when I don't understand something. And it's like I am not entirely sure. It's like I'm not a civil engineer. I'm not an electrical engineer. I don't know if they face similar problems. But the software engineering is, oh my God, is defined by not understanding something, right? So it's like I use so many APIs and I don't actually know what's happening. Yeah. And sometimes I'm even more distraught because then people basically telling me, oh, you don't need to know. That's cool. It's awesome that I don't need to know, but I want to know, right? And often I feel I actually do need to know because otherwise I'm not able to build correct systems end to end. But even if I don't need to know, I want to know because knowledge and understanding give me a lot of confidence. So, and if I don't know something, I am distraught and I'm not confident, right? So it's like confusion is one of the worst states of minds for me. It makes me not want to use something, right? It makes me not want to engage. And one of the reasons why I want this to be dead simple is it's implied to say dead simple to use. It's implied, right? Because that's usually what everybody says. Oh, this is easy to use. But what I really, really want is that it's not only dead simple to use, but also dead simple to understand. Right? Because if I understand something through and through, I'm filled with confidence and I feel good about what I do and I want to engage with it more. And that is what I want to capture with this word of dead simple. And that is what is our core technical value at Resonate, chasing the high of dead simple.
And breaking things down, you particularly, breaking things down into a way where we can have a conversation where we know what we're talking about, right? I appreciate that. Starting from the bottom, building up from there. Yeah. I
No, thank
know
you.
yeah, I know we've been talking so we've been at about it over an hour actually. We've been at this for an hour. I don't have any questions from the chat, but if there's I don't want to overdo it because I know an hour straight will wear us right out. But I want to give an opportunity if there's anybody in the chat who has a question for Dominic on distributed systems, anything, like just literally anything. I want to throw it out there. I want to give you the opportunity.
I can't promise an answer though.
I can guarantee it'll be good.
Oh my God. No, no pressure
You
whatsoever.
never let me down. It doesn't even have
All
to be
right,
about
maybe we get
distributed
lucky.
systems, actually. To be honest, I feel like it could be about your relationship or you know evolution. I feel like
Oh man, that's like no, only distributed systems. That's all I can offer here.
you know I so and before we um, totally officially end, um, what are some future topics that we could potentially cover here on the live stream? I know we've been talking about potentially building an application from scratch as one option, which would probably like a multi-stream
That's yeah.
situation. We wouldn't be able to accomplish that in one stream, but we would do it in depth and we would start from scratch. Um, what are some other topic areas that you're hoping to cover?
So some stuff that I like is so again, I like understanding things, right? But it's natural in software engineering that as a vehicle for understanding things, we use code. A code often has a very low signal to noise ratio, right? There's a lot of noise because the code is not there to speak to you. The code is there to speak to the machine, right? And so what I really really enjoy are minimal samples of something. of some concept or some technique, absolutely minimal samples, because then we basically like try to dial up the signal to noise ratio, make the noise minimal, have a very high signal so that we can internalize the concept. Two concepts that I find really fascinating. Async await is a sequential looking programming model on top of event-driven execution model. So we can implement that from scratch in Python in a few lines of code to just see how that actually works, right? It's like, how does that work that something looks sequential, but then internally we execute it in an event-driven manner. And then you can immediately see, for example, oh, that's cool. I can either execute that on one thread, or I can execute that on like one thread for all executions, or one thread per execution, or something in the middle, right? So you can learn a lot from these like super minimal examples. So that's one of them. Just like where we build our own async await, stripped down, obviously. But where we build our own async await, that's super cool. And just a few lines of Python. And the other one that I like a lot is in durable execution, we often talk about something can suspend, right? So for example, I await on something for 8 hours, for 8 days, for 8 weeks, right? And then resume. But how do you actually implement that, right? So it's like, because once you start a computation on one machine, most environments can actually not like pause that computation and store it in a database. So how do you do that, right?
Without Resonate or with Resonate? Like, would that example include using like a tool like Resonate, or would we be trying to do it without?
From scratch. You do that from scratch. It's a few lines of code. It's really, really cool to see it. Yeah. To see it when it comes alive, where it's like, oh, how do you implement something like resume on top of restart? Right? And there is like almost nothing you need. You need like 10, 15 lines of code. And then you can clearly see, oh my God, yeah, this is how resume semantics are expressed in terms of restart semantics. And we can even define in code with a few lines of code what that means, right? What does that equivalent relationship looks like? And then we can ask the machine to quote unquote prove that this is equivalent. And this is in a few lines of code. And yes, it's a toy. It's not what we're actually using, right? Because there's like, if Resonate was 15 lines of code, we don't have to talk about it. But it's one of these concepts that we're using, and we can replicate that concept in 15 lines of code. You get a massively deep understanding from it. And then you can most dangerous word in software engineering. Yeah. But then you can extrapolate, right? Okay, if I have more complex scenarios, how would I do this? And from there on, you build out. That's why our libraries are as big as they are, which they are actually really small. Go check out our Resonate libraries. And we put so much effort into just a few lines of code. We are prioritizing to have very little lines of code so that we are aiding this whole idea of it's dead simple to understand, to the point where it's not just from an architecture diagram, but if you want to go and read the code, you have a chance because it's only like 500 lines of code.
I share those repos.
Cool.
Awesome. All right. Well, I feel like we're going to tucker you out. If we go on too much, but this was really good, man. We did a solid end to end. Start with transactions versus durable executions.
Seriously.
And made our way to distributed async await and the cool benefits of it provides, and touched a lot of stuff in between. It was
that we really did. That was a lot for the first live stream.
Yeah, it's fun because we've had these conversations where we touch on parts of this, in one go, in like 20, 30 minutes at a time. But that felt like that was like a real natural journey actually to get there.
Awesome.
So this is Dominic Turno and Cully talking about distributed systems, and touching a little bit on Resonate, which is the company we both work for. Dominic's the founder and CEO, And we'll be planning on doing many more of these live streams, hopefully over the next several weeks, touching on a lot of the topics we just talked about. Probably dipping back into this conversation several more times, no doubt, and hopefully developing some cool applications live. I'm sure at some point as well. But yeah, this is really good. Thank you for following along, everybody in the chat there. Really appreciate it, and reach out to us in Discord, which the link is in the chat as well. If you are interested in joining the community, chatting with us offline, off the stream, please jump into that Discord. And there's a growing community in there that's interested in chatting about those things.
Awesome. Yeah, drop in Discord. Let's chat distributed systems.
Cool. All right, I think we're gonna call it then. Everybody have a great Friday. Wonderful.
Yeah, have a great weekend.